So hi, I'm William Young from the University of Chicago, a postdoc, and I'll be talking to you about the power for detecting the presence of set size differences in the CDA. And people who have contributed to this project include Kirsten and Adam, Colin Quirk, Ed Vogel, and Ed O. So what is a contralateral delay activity? It's featured a bit in this symposium so far. It's an event-related potential measured during the retention period of a bilateral change detection task. So in a bilateral change detection task, you are queued to one side of the screen, and you have to try and remember the items on that side of the screen. And what we observe is a sustained negativity over the contralateral hemisphere, so on the side opposite to the queued side. And you can see that in the figure I pulled from Vogel and Makazawa. And we see this negativity over the posterior and occipital electrode, so towards the back of the head. And what we do is we calculate the mean amplitude of this difference wave between the contralateral and ipsilateral electrodes. And this event-related potential has been very useful. It closely tracks the memory load, so it increases in amplitude with increasing set size. So I've just stylized it here. So set size 1 might look like something like this. Set size 2 has a little bit of increased negativity. Set size 3, and then set size 4. And you can see that set size 4 tends to plateau at the same spot as 3, and that's in line with our visual working memory capacity estimates of about 3 to 4 items. And the contralateral delay activity has been a very useful tool in other aspects of visual working memory. So for example, with filtering efficiency and attention, we see, looking at the CDA specifically, high K subjects do not show a CDA for distractors, whereas low K subjects, you do see a CDA with distractors, suggesting there's some sort of filtering elements to visual working memory capacity, binding and grouping. So Luria and Vogel have a stunning example where you have two separate objects coming together and then moving together, which is a huge gestalt cue of common fate. And you see the CDA reacting, changing from 2 into 1. Another thing here is complexity and resolution. So for example, Z and Zhang showed familiarity to Pokemon can increase the speed of consolidation by seeing a rise in the CDA quicker than those who are unfamiliar. And we saw it recently with Johnson's talk on ensemble statistics, and earlier in the symposium with Alon's talk about RSVP presentation. So for review, you can check out Luria et al. 2016 that I've placed there. But one of the more important parts of this talk is power. So just to be clear, I'm talking about statistical power, not alpha and theta power that has also featured in the symposium. So what is statistical power? It's the probability of detecting an effect given the effect exists. So a probability of a significant result given the effect is true. But as scientists, we want to maximize what is referred to as the positive predictive value. So the probability that a positive or a significant finding is due to the true effect and not due to a false positive. So I've written that as the probability of an effect given a significant result. But the positive predictive value is maximized when we increase our statistical power. And when that doesn't happen, it can cause a potential reproducibility in crisis in science that you might have heard about. So other reasons why we need to care about power. It's important that experimenters are sufficiently powered to detect the effect of interest. So researchers consume precious time and resources in conducting these experiments, and also a false negative due to perhaps a lack of power can mean a slowing of scientific progress, as negative or null results cannot be reliably interpreted. Null results are often left in a file drawer just because of how publications are. And we've missed out on figuring out what the actual true effect is. We've missed out on knowing that it exists. And a reason to be concerned about statistical power, we know that increasing statistical power will improve the reliability of our findings, both about true positives and true negatives. But the estimated median statistical power for neuroscience studies has been estimated to be between 8 and 31%, far lower than the standardized 80% that we expect in studies. And this is typically due to small sample sizes. So estimating the number of subjects in trials indeed is useful. It enables pre-registration of sample sizes and study design, and allows us to evaluate whether the experiment is feasible before we actually run the experiment. So in this presentation, I'll be talking about how to estimate power to measure the CDA. And the simple question that I'm trying to answer is, what number of subjects and number of trials is required to be sufficiently powered to detect, firstly, the presence or absence of the contralateral delay activity, and to detect the set size differences in the contralateral delay activity. So I'm using a couple data sets here. The first data set I'll be talking about is the Arnsworth et al. 2015 Journal of Cognitive Neuroscience data set. And in this data set, they conducted a color working memory task with both set size 2 and set size 6. And they ran 171 participants. So this is a huge EEG data set. Of those 171 participants, I pulled out 139 participants who have at least 170 clean trials in both set size 2 and set size 6. And I also used the Nicole Hakim's et al. Data set, the 2019, from PsychScience, where they ran a color working memory task with set size 2 and 4. And in that data set, 31 participants with at least 220 clean trials in both set size conditions, so both set size 2 and set size 4. So I conducted a subsampling analysis, or also known as a downsampling analysis, where we randomly sampled a given number of trials from a given number of randomly sampled subjects. So, for example, we might randomly select 10 subjects and pull 100 of their trials. And then what we do is we conduct a statistical test on that subsample data. And we don't just do it once, we do it 10,000 times, and then we do that for each possible combination of number of trials and subjects that we desire. And what we can then do is estimate the power with the proportion of those iterations that produce a significant test. So that might produce a significant presence or absence of CDA, or a significant set size difference in CDA. So these are the results. This is the heat map for power. So as you get more green, you have increased power to detect, firstly, the presence of the contralateral delay activity. So this is for set size 2, and this is for set size 6. So you can see that we're clearly well powered to detect the presence of contralateral delay activity. It is a little bit easier to detect the CDA in set size 6. So for a typical sample size of n equals 25, you have, in the box I highlighted on the left figure, 30 trials are required for about 80% power in set size 2. And in set size 6, 20 trials are required for at least 80% power. So we're well powered to detect the presence of CDA, but how about set size differences? So the power of set size difference to detect set size differences in the CDA, this is 2 versus 4 from the Hakim et al. Data set. And you can see here, we're significantly less powered. For n equals 25, you need about 220 clean trials to achieve 80% power. And I just want to emphasize that's clean trials. So when we run an EEG experiment, you will need to have more than 220 trials so that 220 survive after fact rejection. So that's 2 versus 4. So for 2 versus 6, the story is even starker and perhaps very surprising to you. You can see here we have less power to detect it. At n equals 25, 80% power is not achieved with 170 clean trials. You can see that as the rectangle, the row that I've highlighted there. And if you extrapolate the curve, so if you follow that second darkest green and follow that along, you'll see we'll need a substantial additional amount of trials to have achieved 80% power to detect the set size difference between 2 and 6. I've also highlighted another cell here that achieves 80% power here. You might need something more like 60 subjects and 150 clean trials, which is far more than the typical sample size of 25. So comparing the power to detect set size differences in set size 2 versus set size 4 compared to set size 2 versus set size 6, clearly power is influenced by the effect size, and set size effects for 2 versus 6 appears to be smaller than 2 versus 4. On the figure on the left, I pulled from Fukuda et al. In his book chapter. You can see that for low K subjects, the CDA drops as you go from 4 to 5 to 6. And so this pattern might suggest that the effect size is being reduced. And you can see that one reason for this is set size 6 may overload the visual working memory system and recruit filtering processes and things like that. So one thing that you might do instead of looking at 2 versus 4 or 2 versus 6 is you might look for a design that targets set size 1 versus set size 3 instead. So some limitations about these subsampling analyses. These analyses are restricted to a maximum of 200 or 220 clean trials, but we have conducted preliminary simulations predicting beyond these limits. So more to come on that. And how well these analyses extrapolate relies on the generability of these data sets. Given that these are larger than standard EEG data sets, I'm inclined to assume that it has more external validity, but one way to improve this is to perhaps do a mini labs kind of thing where we collate a big data set. And another way to improve power is not just to use number of subjects and number of trials, it's to actually just improve the precision of the measurement of the CDA. I just wanted to point out a recent look at our journal article, which introduces a measurement for ERP data quality. So some takeaways: typical numbers of subjects and trials for contralateral delay activity experiments may be underpowered when detecting set size differences. The size of the effect is critical when planning numbers of subjects and trials in any experiment, so you might need to improve your experimental design to increase the power, such as looking at 1 versus 3 rather than 2 versus 4. And we hope in the future this subsampling analysis will enable principled estimates of power, ensuring better chances of detecting the effect. And again, we have preliminary simulations beyond the number of subjects and trials that we hope to publish in the future so people can do that. So lastly, thank you to my collaborators, Kirsten, Colin, and the Eds, and the rest of my lab. And I'd love to hear your feedback if you want to send me an email or follow me on Twitter.